Thank you, Jörn, for this very nice introduction. You've already heard quite a bit about knowledge processing for robots in the first 3 days of this fall school. But in probabilistic knowledge processing, things work in a slightly different way, as we will see. And I want to begin this lecture with a quote that I found in the Museum of Science in Boston, Massachusetts. And the quote is from Pierre-Simon Laplace, and he said about probability theory is nothing but common sense confirmed by calculation. So I like this very much because apparently Laplace considers probability theory as a mathematical vehicle to do common sense reasoning. And common sense is defined, I took this from Wikipedia, this definition. It's as the basic ability to perceive, understand, and judge everyday matters that is shared by nearly all people. So everyday matters, this brings us right into the middle of this EASE project, right? Everyday matters, everyday activity. And our everyday activity and everyday matters are characterized by a lot of imperfection and noise. So when we carry out certain actions, then they will not always succeed. We do have incomplete knowledge about our world. So there is a lot of noise, inconsistency, and non-determinism and randomness. And everywhere where we have this kind of ignorance, then probability theory kicks in. So our probability theory is about all the things that we do not know, but still want to reason about. Okay, but step by step, from the very beginning. So Michael already, in his introductory lecture, showed this knowledge representation hypothesis in which we have a certain representation of our real world in some formal language. Typically, this is some a logic-based language, and we have a knowledge base consisting of sentences that allow us to reason how we think, or how our model tells us how the world evolves. So we can use this knowledge base to draw conclusions about how the world works. And ideally, well, if we draw a conclusion and we come to another set of sentences, then if the theory is correct, the real world will also comply to this representation and also convey this new knowledge. However, what happens if our theory is incomplete? If we do not have full, complete knowledge? What if our representation of the world at first is uncertain because, well, our sensors are maybe noisy? In such cases, we cannot use logics. Logics is not well suited for representing these kinds of uncertainty. Indeed, when we have only like a slight inconsistency in our logical knowledge base, we cannot do anything with it. But we still need to act, right? A robot cannot say, well, I'm not doing anything, come back on the other day when my knowledge base is consistent again. This cannot be. We have to act. So we somehow have to take into account explicitly this uncertain nature of the world. And here we have probability as an appropriate mathematical framework. And typically, a probabilistic knowledge based system consists of 3 components. We have a representation language in which we declare some rough structure of the model, and we have observations And together with this dependency model and the observations, we come to a probabilistic model through machine learning. I'm not going to talk a lot about machine learning because there is, I think, a whole extra session on machine learning. But I will focus in this lecture on the representational part of probability. And having such a probabilistic model, we can ask queries to this model and get back a quantified answer about which of these queries hold and which not. Okay. So, I want to give you a very, very brief primer in probability theory. This is just 2 or 3 slides because I think most of the stuff everybody knows in this room. So let's go through this very quickly. A very central concept in probability theory is the concept of a random variable. And a random variable is a term in a language which can be substituted by a value from a certain domain. And those random variables, the values of those random variables are exhaustive and mutually exclusive. This means that in every possible world, a variable has exactly one value. Okay. And if we have a lot or many of those random variables, then we have a possible world given by a complete assignment of every variable to precisely one value. This we define as a possible world. And this spans a set of possible worlds which we denote with this calligraphic X here. This is called the universe. And further, just for the next slide, if we say that a certain variable xi has the value v in the world x, we denote this with this symbol of logical entailment. Okay? And then we can define a probability space consisting of a set of variables, which we consider, and a function mu that assigns to every possible world a positive real value. So this is called the probability mass. Okay? And we can, given this set of variables, the set of possible worlds, and the probability mass function, we can compute our degree of belief for every possible proposition f by just summing up the probability masses of all possible worlds in which f is true, divided by the sum of all probability masses. Okay, so that's very basic. There are 2 kinds of probabilities typically. The first and simplest one is an unconditional probability. This is a probability, a degree of belief without further information. For example, the probability that somebody has headache, that the variable headache is true. It's a Boolean variable, and this can be assigned a probability of like 10%. This is a Boolean variable. There can also be multinomial variables such as the weather, which can take more than 2 values like sunny, rain, cloudy, and snow. So we have a set of mutually exclusive Boolean propositions. And those can be represented in a table, right? We can enumerate all possible values for every variable and put in the respective cell of the table our a priori or unconditional probability. A second kind of probability is a conditional probability. So, because when we have new information, this information might alter our beliefs in certain propositions. For instance, when a priori probability for headache is only 10%, but we know that a person had some beer the evening before, then this probability of headache might increase. Okay? So the knowledge that a certain event has happened changes our degree of belief. And more formally, the conditional probability is defined as this fraction of the joint probability of A and B over the a priori probability of B. And intuitively, we can think of it in the set diagrams if we want to query for a probability of an event A. When we know that B has happened, then we can look at the intersection of A and B. So we don't have to look in this area because B has not happened here, and divide it through the set of all B events. And then we get intuitively a probability for A given B. And with this definition, we can come up with a couple of calculation rules and theorems. For instance, this rule allows us to split a joint distribution into two factors, a conditional and a prior. Okay? And applying this rule twice results in a very important theorem, the so-called Bayesian theorem. This allows us to change the directions of inference, for instance, make a causal inference, a diagnostic inference, and vice versa. Okay, so this was very basic stuff. So the question is, how can we represent these probabilities? I already mentioned that we can come up with a table in which we put in every cell the respective prior probability of the joint, and from this joint distribution we can calculate every conditional probability we can imagine. Okay, this is possible. However, is this practical? And the answer is, of course, no. Why? Because this full joint probability table grows exponentially in the number of variables that we consider. Okay? So this table gets really, really big very, very fast. So it's not only hard to represent because we run out of memory. Memory is too small. But it's also hard to determine because somehow we need to come up with the numbers. So if we have exponentially many numbers to estimate, we also have to conduct exponentially many experiments to come to the numbers, right? So this is twofold, very difficult. And the question is, of course, is there ways to come up with a more compact representation and more efficient methods to reason about this? And the bad news is no, there is not. At least not in full generality. But there is many, many special cases in which we can exploit certain problem structures that allow more compact representation and more efficient reasoning. Okay. What can we do? Suppose we have a large number of random variables and we want to represent them. So what can we do? For example, we can use the product rule that we just had a few slides ago and split the joint distribution into single factors. Okay, so we can do this. So we have more but smaller probability distributions. Did we gain anything? Unfortunately, no. We still need the same number of table cells or numbers to represent this distribution. But if we exploit our knowledge about the structure of the problem, for example, if we knew that the variables B and C are independent, then we can cancel the C from this distribution, and this distribution is indeed smaller than this one. Okay. So by exploiting domain knowledge, we can reduce the complexity of our models. And that's the very idea of probabilistic graphical models. And everyone who took AI1 or AI2 is very familiar with this very simple example, where we have 5 variables, 5 Boolean variables, And in such a Bayesian network, for every variable, we introduce a node in a graph, right? So we have a Boolean event of a burglary happening and an earthquake happening and an alarm of our house goes off, and we have two neighbors, John and Mary, and they promise to call us when they hear our alarm going off. Okay. And a Bayesian network then consists of directed edges that represent causal relationships of those variables. Okay? So the burglary is a possible cause for the alarm going off, as well as the earthquake. And hearing the alarm causes John to call us and Mary to call us. Okay? So we put in this Bayesian network direct causal relationships in the form of directed edges. And to quantify these relationships, we also put conditional probabilities for every node conditioned on its direct ancestors. Okay? So here we have a probability that Mary calls given that the alarm goes off, and the probability that the alarm goes off when a burglary happened but not the earthquake. Okay. Okay, so this results in a directed acyclic graph, a graph which has no cycles. And nicely, the joint distribution over those 5 variables factorizes according to the topology of the graph. Okay, so we have J given A. John calls given the alarm times Mary calls given the alarm times A given B and E, and the a priori distributions over B and E. Okay, so the Bayesian network, did we gain anything? So from our naive full joint probability table with 2 to the power of 5, 32 entries, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries. So we saved 60% representational complexity by exploiting our knowledge about the problem structure. Okay, cool. But what if we do not know the causal structure? If we do not know what causes what? In a medical diagnosis system, for instance, it's not always clear which are the causes of some disease, right? What if there are mutual dependencies? If one variable influences the other and the other way around? Is there in Bayesian statistics at all such a thing like unilateral dependencies? Is it possible that one variable depends on another variable but not vice versa? Turns out, no, this is not possible. So this thing with causes and directed edges is a bit subtle. And the question is there maybe a more intuitive way of representing these dependencies? Okay, and well, there is. In a Markov random field, the dependent variables are grouped in fully connected subgraphs, which are called cliques. So we have dependencies among the alarm, burglary, and earthquake, and they are grouped in this fully connected subgraph of 3 nodes. This is a maximal clique. And there is another 2 cliques, which is the John, between John and the alarm, and Mary and the alarm. And the distribution now attaches to every maximal clique in the graph. Oh, no, okay, so for better readability, sometimes these cliques are made explicit by these black squares, and this is called a factor graph. And a factor graph because in the Markov random field distribution, every clique corresponds to a factor given by a so-called clique potential function, which maps the current state of the clique to a positive real number. Okay, so for this factor, we have the domain of the burglary, which is Boolean, of course, true, false, and the earthquake and the alarm mapped to some positive real number. And according to the other two factors, there is only two variables going in and also a real value going out. Okay, so what's the probabilistic semantics of such a Markov random field now? So the probability for a specific possible world, X, is given by the product over all clique potentials evaluated in the current state of the clique in the world X. Okay, so this gives us a product over these real numbers. And this product is, of course, not normalized. Not necessarily. It can be, but it's not necessarily. So we have to ensure that it's a proper distribution by dividing by the so-called partition function, which is the probability mass of every possible world, as previously defined. Okay. And sometimes, because this is also a bit tricky and it might also be a bit complicated to figure out what the cliques in the Markov random fields are, one makes a model assumption that this distribution, the product over all clique potentials, they take the form as a log linear model. This means that the probability mass is an exponential and exponentially weighted sum of Boolean features. So we introduce a Boolean feature for every clique, which maps to 0 or 1. If the feature is there, it's 1. If it's not there, it's 0. And we attach a weight to this feature. Okay. This is a log linear Markov random field. So these are two very famous families of representational formalisms in probabilistic knowledge representation. Bayesian networks on the one hand, Markov networks on the other, and there is many examples. One of the the most simple is maybe naive Bayes, which probably everyone has heard of. There is a discriminative counterpart, which is the logistic regression. Then there is generalizations of that, where the class variables depend on each other in sequences. This is in the Bayesian network case, it's called hidden Markov model. In the Markov random field is a conditional random field, and there is more and more generalizations of that, and many of them. But the problem is, typically, we always have to know in advance the number of random variables we like to consider. The number is typically always fixed, or the structure is very narrow and very tight. So this limits the expressiveness of this formalism, unfortunately. So we are in a classic dilemma. We saw first order logic as a very expressive formalism and to represent very complex relations that also allow to universally quantify statements that apply to every kind of entity. But the first order logic formalism could not deal and address the uncertain nature of the world. And on the other hand, we had the probabilistic graphical models that are very well suited for representing uncertainty and dealing with uncertainty, but they only allow for limited complexity. So this is a typical case of Murphy's law of conservation of misery. There is always this trade-off between this complexity and expressiveness and the ability to deal with uncertainty. And the one way out of this dilemma is tackled by the field of statistical relational learning, which aims at combining these two worlds, the expressiveness of first-order logic and the ability to deal with uncertainty. So, one example of such a formalism that I want to introduce today is so-called Markov logic networks. And in Markov logic networks, we have a formalism or a representation language which allows constant symbols that allow us to identify objects in the world, such as Adam or Steve, like identifiers for entities in the real world, or abstract entities such as 42. And there are predicates which allow us to attribute certain properties to objects in relations. For instance, that the age of Adam is 42, or that Steve has cancer. I don't like this example, but it's very illustrative. Okay, but the predicates can also put entities in the real world into relations. So we can also say that Adam and Steve are friends. Okay, and those propositions, they serve as the basic variables to construct a probabilistic graphical model. So having these atoms in first order logic, we can also make universal statements about entities in the world. For example, we can use quantified statements like make a statement that smoking causes cancer. In logics, this could be done with for all x, if x smokes, then x has cancer. Of course, this is not true for every smoker, luckily, right? But in logic, it must be true. If not, then the whole knowledge base would collapse. In Markov logic, we attach to this logical formula a real valued weight, which determines the strength of this formula. Okay? So we allow exceptions, which is not possible in pure logic. Okay. And the idea is then that the more true instantiations of a logical formulas there are in a possible world, the more it contributes to its probability, right? So more true formulas, higher probability. Okay, let's do this a bit more precise. So Markov logic network is a set of pairs Fi, Wi, where Fi is a formula in first order logic and Wi is a real valued weight. Okay. And we can now set up our knowledge base of weights and formulas. For instance, for all x, not smokes x. In first order logic, this would translate in nobody smokes. Okay. But in Markov logic, we can put a weight to this in front of this formula, and we have a different interpretation, namely, most people do not smoke. Okay. Likewise, we can say that for all x, not cancer x, means nobody has cancer. This is not true in the real world, but in a purely logical formalism, this must be true. In Markov logic, we put a real valued weight in front of it, and the interpretation becomes most people do not have cancer. Okay? You can also say that for most people, the relation does not hold. So, most people are not friends with each other. Here we again have our relation of the smokes attribute and the cancer attribute. So, smoking causes cancer. This is again weakened by this weight of 1.5. And we can say that for all x and y, if x smokes and x is friends with y, then y also smokes. So friends tend to have similar smoking habits. Okay? And as a hard formulas are also allowed in Markov logic. They have infinite weight. Then we can say everybody is friends with themselves. Okay. Good. So what's the probabilistic semantics of such a Markov logic network? So we have a set of predicates, like for instance, vegetarian, female, and orders a certain dish. And the arguments of those predicates, they are typed, right? Okay, so every person argument shares the same domain. And we have a set of domains. In this example, there is two persons, Alice and Bob, and there are two dishes, pizza and pie. And we can then create from the predicates and the domain a set of random variables by substituting every argument in every predicate by every value in every domain. So this predicate vegetarian and the person domain yield two atoms, vegetarian Alice and vegetarian Bob. So this is a substitution of all variables by constant symbols. So we obtain a set of random variables given by ground atoms. Okay, we have grounded Boolean propositions. Those can be either true or false. Okay, and those make the random variables for a so-called ground Markov random field, which we will, I think see on the next slide. So, given this set of variables x, ground atoms, we have a set of possible worlds, which is 2 to the size of this set, of course, right? This many possible interpretations we have. And we do the same for all formulas. We replace every formula by all values from the respective domains, and we obtain a set of grounded formulas. So there is no variable anymore in any of the grounded formulas. Okay. And then the probability of a specific possible world, this is a truth assignment to all of those variables, as follows. This looks a bit wild, okay, but this is the most complicated slide. It's not so difficult. It's actually pretty simple. Where is my pointer? Here. Okay, so here we have this MLN given by a set of formulas and attached the weight, okay. We just said that the number of random variables, or the set of random variables, are given by the grounded atoms, given by the predicates and the domains. This is this x, okay. And we have a set of ground formulas and the ground formulas, they represent the clique potentials in a Markov random field, which map from the respective the set of respective ground atoms to a real value. Okay. And this is given by an exponentiated feature where the feature function is 1 if the respective ground formula evaluates to true, and it's 0 if it's false. Okay? So, this looks a bit complicated, but the interesting thing is here, the probability of a specific possible world in the Markov logic network is given by the exponentiated sum of the number of true instantiations of every formula multiplied by the respective weight of the formula. Okay? So this intuitively corresponds to what we said in the beginning, that we want to have a model where the probability of a specific world grows with the number of true formulas. Okay? This is what we have here. The more true instantiations a world has, the larger the contribution of the respective formula is. Okay? And we can use this distribution to actually do inference or reasoning about any aspect in this model, given any other aspect as evidence. So Q is an arbitrary query, E is an arbitrary observed set of ground atoms. And we can then compute the probability of this query by establishing this ratio of the probability masses of all the worlds where the query and the evidence are both true, and the probability masses of all the worlds where only the evidence is true. Okay? According to the definition of our conditional probability. Okay, great. So let's have a look at some examples of what can we do with Markov logic networks. This is work that has been done in this group in the Institute for Artificial Intelligence here, and we applied Markov logic networks in the field of robot perception. So the problem is that we have as input here this noisy 3D point cloud coming from the Kinect of the robot, and we have a number of clusters in this point cloud. Those are noisy, of course, and they have different visual cues. And the question is, can we merge the output of several different perception algorithms in an MLN to come up with a probabilistic knowledge base which can be queried in any different, with respect to any arbitrary aspect. And this is how we did that. We established, I think you will learn about this in Friday's lectures on robot perception. We have this raw input, applied some clustering to extract the point clouds of the single objects, and then ran multiple independent perception algorithms on these point clouds, and those served as annotations which are attached to every cluster in form of these logical atoms. For instance, a color annotator, this procedure specialized for detecting colors, annotated the cluster C1 that it has yellow components. A shaped classifier detected that this must be a box. And Google Goggles annotator detected a Dr. Oetker brand logo on this box. Okay, so these are evidences which come from perception algorithms, and they are all merged into a Markov logic network, which is then used to query the to query the identity or the category of the respective objects. Okay, so here you can see a snapshot of a video showing the system in operation. You see the different annotators in the form of ground atoms in this MLN language, and in blue the final output of the Markov logic network. Okay, so this is an intermediate summary of MLNs. They have been introduced as a combination of first-order logic and probability theory, marrying the benefits of the two formalisms, and indeed it is one of the most powerful and most impressive, most expressive representation formalism that also subsumes all the other probabilistic models that can be somehow reduced to either Bayesian networks or Markov random fields. So Markov logic networks can be regarded as a template language for constructing probabilistic graphical models. Okay, so now let's come to the second part, which is the fourth part of this talk. As the title says, applications to natural language understanding. So if we, you have already seen it on Monday in the demo session upstairs, that if we want to endow robots with the ability to execute natural language commands, we see that transforming this natural language instructions into executable robot plans needs a lot of knowledge. For instance, if we have this task of neutralize 5 drops of hydrochloric acid, then there is a lot of reasoning steps to be done. So first of all, the robot needs to know what is actually meant with this string, basically, right? It's a string. And it needs to know that it refers to a neutralization process where there is an acid substance involved, namely the hydrochloric acid. So it needs to know what is the alkaline counterpart, which is in that case the sodium hydroxide. But this is not mentioned in the instruction, right? Then it needs to know that in order to achieve this neutralization, the sodium hydroxide must be added to the hydrochloric acid. And eventually, that adding such a small amount of a delicate substance like sodium hydroxide requires a pipetting action from the container holding the sodium hydroxide to the container holding the hydrochloric acid. And eventually, this action must also be executed. The pipette must be grabbed, aspirated the sodium hydroxide from the respective container, and releasing 5 drops into the gold container. Okay. So acquiring, so we have seen this, that executing these instructions is very knowledge intensive. And one way to acquire this knowledge is to look at large collections of instruction sheets on the internet. But they are made by humans and also are intended for human use. So there appear quite some challenges. For instance, those instructions on the internet, they are very vague and incomplete. For instance, it does not say that, which utensil to use to cut a pizza, or which utensil to use to slice bread. There is also words referring to other words in the sentence or even in other sentences. There is ideally, there should be a possibility to transfer knowledge from one document to another. For instance, when a document says serve the pizza and there is an instruction sheet for how to serve food, this should be adaptable to this scenario of serving pizza, right? Or the plan for serving juice should be adaptable to serve wine as well. There is multiple steps. It's not only atomic actions, it's compositions and sequences. And ideally, there should also be an action refinement, because those instructions are very abstract typically, and they can be made more specific by looking up a respective document. For instance, here we have a pizza preparation task, and this can be looked up in some other recipe for making pizza. Okay. And in our work, we assume that we can tackle all of these problems by representing a probability distribution over all sequences of executable plan steps, just denoted by this p to the natural numbers. All sequences conditioned on natural language sentences. This is the lambda. And we can then, having such a probability distribution, we can then query it for the most probable plan from all sequences conditioned on a specific instruction. Okay. And to achieve that, we came up with this concept of what we call probabilistic action cores. And probabilistic action cores consist of a set of action symbols A, like neutralizing, adding, or pipetting. This is a symbol identifying or representing an action. There is also a set of semantic relations, so-called action roles, R. And they assign a semantic role to every entity which is affected by the respective action. For instance, there is an acid substance in a neutralization action, and there is an alkaline substance given by the hydrochloric acid and the sodium hydroxide.
So how are these relations defined?
Sorry?
How are these semantic relations defined?
This is a good question. So ideally, these semantic relations, they should interface the robot plans. So this is a design by contract principle. We will see an example on one of the next slides, where the semantic roles here are actually the parameters, the abstract symbolic parameters of the executable robot plan. I will show an example in the next slide. So, yeah, so these are the semantic relations of every action symbol, action core. And we also, the symbols in PRAC are not only plain symbols, but they are organized in an upper ontology. So here we have an is-a relation, which the subsumption relation, which groups symbols into semantic categories, where this top symbol refers to the set of all concepts, and this square subset equal symbol is the subsumption, the is-a relation. And here you can see that given this semantic network of actions and objects and relations is just a natural language instruction only serves as very little evidence in this more complex semantic network of objects and actions, and we want to learn or represent a probability distribution over these relational models, okay? To be able to infer every kind or any kind of information that we need to know in order to execute the plan. And for that we use Markov logic networks, okay? Apart from that, we also want to use a set of instruction sheets, recipes that can come from WikiHow, from the internet, or from cookbooks, for example. Okay, so what's the benefit of having a probability distribution over these semantic relational networks? So here we can see two example queries. For example, if we have an instruction, add 3 drops of sodium hydroxide, we could ask the Markov logic network, what should I do with which object? So, for example, we have this action core adding in this case. We have a set of semantic roles, like a quantity, a theme, source, goal, and so on. And we could then ask, there is an object O1, which is of type drop, and an object O2, which is of the type sodium hydroxide, NaOH. What is the most probable role assignment to O1 prime and O2 prime? And the result is then ideally O1 prime equals O1. So the quantity is given by a drop, and the theme is given by the sodium hydroxide. So this is an example of how we can ask for a role assignment in a given sentence. But we can do more. We can also query for things that are not explicitly mentioned in the instruction. For example, neutralize the hydrochloric acid. Then we could ask, what should be used as an alkaline counterpart? Because we know that there is an object HCl of type HCl. This is a concept symbol in the ontology. We know that this object HCl fills the semantic role of the acid substance. But we also know that there must be an alkaline substance as well. And for that we can establish or introduce a Skolem constant of some entity S that fills this alkaline substance role, and then query for the most probable type of S. Okay, and this is then the sodium hydroxide. So, if we can, given this natural language instruction as evidence, we can basically compute the most probable completion of those semantic networks. And this is coming back to your question. This inferred knowledge pieces can be used to fill in the parameter slots of attached robot plans. Okay, this is the idea. So, yeah, more formally, we have a set of actions A and roles and concepts, and we can represent a role assignment by a tuple of an action symbol, a role, and a concept. For instance, the destination role of a filling action is filled by an object of type cup. Okay, and we can also and we have an executable plan call, which is also a role assignment, but with a subset of actions. And those are those actions which the robot can actually execute. They have a mapping from an action symbol to a robot plan with the respective plan parameters. Okay. Okay, and the goal of PRAC is then to represent a distribution over all sequences of role assignments conditioned on natural language sentences. So we have a conditional distribution of role assignment sequences given natural language instructions under consideration of an upper ontology and a possibly large collection of recipes, of documents from the internet. And having such a distribution, we can then infer the most probable plan given a natural language instruction, such that every role assignment in every step of the plan is executable. Okay, so this is the inverse set of executable plans. So every role assignment in the plan is disjoint with the set of non-executable role assignments. And as it is clear that this distribution is infeasible to explicitly represent, we need a factorization to make it tractable. And we have basically these 4 factors. In the first factor, we infer, given the language and the upper ontology, a most probable sequence of action symbols. The second, so this is the action core inference. The second factor, conditioned on the result of the first inference, given the action sequences, we can infer the role assignments that are given in the instruction. So this is a kind of inference of this type. So we infer what is given in the role assignments that are mentioned or given in the natural language instruction. Knowing the action core and knowing the given roles, we can then compute a distribution of the things that are missing. Okay, so here we can infer all the role fillers that are not explicitly mentioned in the instruction. That's this type of inference. And as a last step, because not all of those complete role assignments might be executable, we want to compute the most probable executable refinement. So, for example, if we have an instruction to neutralize, let's say to add the hydrochloric acid, then this is not directly executable because an adding action is too vague and too abstract to be directly executable. Because depending on the object that you want to add, you might want to execute the action in very different ways. So liquids can be added by pouring, drops can be added with a pipette, water can be added by operating the tap, and so on. So these action specifications, they need refinements. Okay. So this is how we use this distribution over sequences of role assignments to infer the most probable executable plan given natural language, an upper ontology, and a set of instruction documents. One of the key concepts in this Prax system is that it is able to use the upper ontology to abstract away from single instances of events or instructions to more generic patterns. For example, if we have 2 instructions, fill the cup with milk and pour water into the cooking pot, then we can observe that the role fillers of these actions, they represent clusters in the upper ontology. For example, milk and water are both subclasses of drink or liquid things. Likewise, the destination role of those 2 instructions, like the pot and the cup, they are both They are both subclasses of food vessel or containers. And by having a probability distribution, also taking into account this subsumption relation, the system is able to transfer knowledge of known objects to objects that it has never seen, for instance, juice, because they are very closely related in the taxonomy. Okay, and to this end, we use a measure of semantic similarity, which is basically based on the relative length of the paths connecting two concepts in the ontology. So the shorter the shortest path connecting coffee and milk, for instance, which is via the beverage concept, the shorter this path is, the semantically more similar these two objects are supposed to be. In contrast, if the path is very long, for instance, the concept coffee and the concept cup, this path is, the shortest path is over the most abstract concept, the entity. Then this path is long, and this similarity is, or those two concepts are assumed to be very dissimilar. And there is very efficient heuristics to compute this. So in Prague, we can condition on the similarities that we can efficiently compute from the taxonomy. And for example, if we have a training set of two instructions, like fill a glass with milk and add a cup of milk, and we have three concepts involved, which are highlighted in green here. One is the glass, which is subclass of a container. We have the milk, which is in this area of substances or liquids. And we have this concept of cup. And this is slightly different with respect to its semantics to the glass, because in this second instruction, add a cup of milk, the cup refers to a unit of measure and not to a physical container, right? So this is why those two concepts are very far away from each other. Okay, so having learned a Markov logic network with only these three concepts, we can then be able to we are able to do reasoning about basically all concepts in this taxonomy without having ever seen them. For instance, if we condition on the filling role, the destination role of a filling action, and we compute the distribution over all concepts in the taxonomy, then we can see that from originally this glass concept, all the concepts in the neighborhood, which are semantically close to a container, gain probability mass. If we instead condition on the theme of the filling action, then we see that all the concepts in the taxonomy which are semantically close to milk gain a certain amount of probability mass. Okay. So this is how MLNs and a taxonomy can be used to transfer knowledge to new unseen concepts. Yeah, so using an ontology and a taxonomy saves us representational complexity. However, if we want to complete or compute completions of instructions, we would still need to represent all the possible combinations of all objects, actions, and role assignments. And that's still not feasible. But If we look at documents that we found on the internet, we see that we can find completions of certain instructions in other documents. So for example, we can refine this set the table action by substituting it by the sequence of another recipe for setting the table. Or we can find the answer to the instrument relation of this cut a pizza action in some other document. Okay? So why not using this large corpus of natural language instructions directly to approximate a probability distribution? So this is how we can do that. We assume that every recipe consists of a title, a header, and a body. And we assume that the title of a recipe can be equivalently replaced by this set of instructions. Okay, so it effectively achieves this goal. And the second assumption is that after a finite number of such substitutions, we arrive at a situation where all the instructions, or all the instructions or actions are executable by the robot. And we do that by assuming, or the basic assumption is that the probability of a role completion, so this RM or our missing role this is a role assignment for the roles that are missing, given a partial role assignment, this probability is somehow proportional to the most similar instruction that we find in the cookbook or in WikiHow. And this makes sense because if you're preparing tomato soup, for instance, and the cookbook says that you should season the tomato soup with salt and basil, then you have good reason to believe that this is a good completion for your instruction, right? So we can compute these completions of role assignments very efficiently by querying for the most similar instruction that we find in WikiHow and bringing over the missing roles to the new situation. For instance, instruction is season the steak, and it does not specify the spices. Then we can look up in WikiHow or in a cookbook a flavoring action which has been performed on spare ribs, and in the spare ribs context salt and pepper has been used. And then we can bring these role completions to the new situation and then try out if salt and pepper is an appropriate seasoning for steak. Okay. Without the need of computing the entire distribution. So that's a very efficient approximation here. But not only for role completion, we can also apply the same principle to refine role assignments. For instance, also here the assumption is that the probability of a role assignment is somehow proportional to the most similar instruction or recipe in the cookbook or in WikiHow. And we can do in the same way query for the most probable how-to title, which is most similar to our current role assignment, and then project all the single steps from this instruction, replace serving food by all the single instruction, and then adapt it by substituting the missing roles. Okay, so this was an introduction to the PRAC system, and this at the same time concludes my presentation. I hope I was able to convince you that probability theory or probabilistic graphical models are a very appropriate way of representing uncertainty, and that they are actually necessary for common sense reasoning. And yeah, so I hope you enjoyed this lecture, and I'm happy to take your questions. Thank you. Question. Sorry?
You mentioned about calculating similarity between instructions, like do you use cosine similarity?
You mean the similarity between complete instructions, not only concepts. There we use the harmonic mean of all concepts appearing in the instructions. Right?
Is it a major defined or defined?
This is what we thought is appropriate. There might be better similarity measures, yeah.
Also for the naming, why do you call it as fuzzy Markov logic network? I mean, to make it fuzzy, I think there should be some degrees in
Yes, the reason why we call this fuzzy MLNs is that we refer to the similarity here, or no, we refer to an unknown concept in terms of its similarity to the known concepts, right? So we assert in the evidence that, for instance, the cup is not a cup, but it's some object which is very similar to a glass. It's very dissimilar to the milk, and it's even more dissimilar to this cup. Okay, so this is a quantified statement, like a numeric, subsymbolic statement. But Markov logic networks, in their original form, they do not support like real valued variables. Okay, they only support Boolean variables. So we came up with this extension of fuzzy MLNs that allow also real valued degrees of truth in 0 to 1. Right? So it's a generalization, actually. Yeah. Other questions? There's a question.
So you said you would infer from spicing or seasoning asparagus how to season a steak. What if you didn't find asparagus with salt and pepper, but I don't know, gingerbread with cinnamon and sugar? That wouldn't make for a very tasty steak.
Yes, we cannot fight that because it is still a statistical model, right? We do not have causal models of taste, right? But we can only make suggestions that this has previously worked well in a similar situation. You might want to try it out here as well, right? Okay.
No question?